Well, I take up another interesting problem on rotational mechanics. This is from a famous physics book, Concept of Physics by H.C. Verma. A very important book for the study of advanced level physics, be it JE mains, advanced or NEET. This is the first volume, 10th chapter problem, exercise 68. It says a meter stick weighing 240 gram is pivoted at its upper end in such a way that it can freely rotate in a vertical plane through this end. The figure is attached here. A particle of mass 100 gram is attached to the upper end of the stick through a light string of length 1 meter. Initially, the rod is kept vertical and the string horizontal when the system is released from rest. The particle collides with the lower end of the stick and sticks there. Find the maximum angle through which the stick will rise. Please note this word, that particle collides with the lower end of the stick and sticks there. Well, again, while discussing this problem with my students, I have seen the dilemma of the students as to what method should they apply to solve this problem. Some says total mechanical energy is conserved, we can apply that. Some says that linear momentum is conserved during the collision. So let us apply the principle of conservation of linear momentum to work out the problem. And some says that angular momentum is conserved about the pivot. From there we have to proceed and work out the problem. Well, yes, what quantity is conserved here and what is not, that we must understand very clearly. First of all, as I said, that the particle sticks to the end of the rod is an important part of this problem that clearly shows that the collision is perfectly inelastic between the rod and the particle. So, kinetic energy cannot be conserved during this collision, and hence throughout the motion of the particle plus rod, we cannot apply the principle of conservation of energy. Next, whether linear momentum is conserved or not, that is another important question. Here, we know that if there is an external impulse or force acting on a system of particle, then the linear momentum of the system is not conserved. If you look into this problem, there is indeed an external impulse that comes into play at the pivot on the rod. When the particle hits the rod, immediately the whole rod has a tendency in this diagram to move leftward, to translate leftward, and therefore the rod pushes the pivot, and the pivot in turn exert an impulsive force or an impulse on the rod. Since pivot is an external object, to our system of particle and rod. So this external impulse, presence of this external impulse prohibits the application of conservation of linear momentum. On the other hand, since this impulse passes through the pivot, so its torque about the pivot is zero. Not about any other axis, only about pivot. And hence, the angular momentum of our system of particle plus rod is conserved, but only about the pivot. That we must very clearly understand. That it is a question where we can apply only the principle of conservation of angular momentum during collision about an axis passing through the pivot. So, if we assume that the particle strikes the rod with a velocity v, let us try to find out the expression of v. Before that, let me identify the different quantities we are dealing here. M is the mass of the particle, which is 0.1 kg. I write capital M as mass of the rod, which is given as 0.24 kg, and L, the length of the rod as well as that of the string, is 1 meter. Now, if the particle strikes the rod, the end of the rod, with a velocity v, then from the principle of conservation of energy, that is gain in kinetic energy of the particle, half mv square is equal to loss in potential energy of the particle mgl, we immediately get the value of velocity with which the particle strikes the rod, which is root under 2gl. Now next comes the application of conservation of angular momentum. As the particle sticks to the rod, they start moving about the pivot with an angular velocity omega. The two together starts moving with an angular velocity omega, such that the conservation of angular momentum demands that I omega is equal to the initial angular momentum of the particle about the pivot, and that is mv into L. Now here I is the moment of inertia of the rod plus the particle, so I can write I is equal to, for the rod, 1/3 ml square plus the particle ml square, and that can also be written in simplified form as L square taken common, capital M by 3 plus small m. Now this is the second equation that we had reduced, and the next equation, so far as the subsequent motion is concerned, and if we assume that the system rotates to the maximum angle theta, that is what is wanted, then after this collision onwards, the total mechanical energy is conserved. During collision, it is not conserved, but after the collision onwards, the whole system is moving under gravity, a conservative force, so total mechanical energy is conserved, And therefore we can write that gain in potential energy of the system is equal to loss in kinetic energy. Now, if it rises up to an angle theta, then for the rod, the gain in potential energy will be mgl by 2 into 1 minus cos theta. For the particle, it will be mgl into 1 minus cos theta, and that will be equal to half I omega square, where I we have already defined the moment of inertia about the pivot of the system of rod plus particle. Well, let me simplify this equation to find out this theta. I can write this as GL taken common into 1 minus cos theta whole into capital M by 2 plus small m is equal to I write it for sake of quick calculation as I omega whole square by I, so that I can further write it as half I omega being mvl, it is m square v square l square by I, which is l square into m by 3 plus m. In my next step, I can simplify this to GL into 1 minus cos theta into capital M by 2 plus small m is equal to, well, look here, the L square cancels out, and I can write it as half m square, and now I put the value of v as root 2 gl, so v square is 2 gl divided by capital M by 3 plus small m. Now, please notice an interesting thing here, and I did not put the numerical values in intermediate steps, which I generally advise my students also, that don't put the numerical values in the intermediate steps. Go on working out the problem till you get the final answer in terms of the notations given. Like here, you can see that G cancels out on either side, the L cancels out on either side, and you get 1 minus cos theta is equal to, well, it is 2 also cancels out if you check. It is m square by m by 3 plus small m. Now, here let us pause a bit. The most interesting part of not putting the intermediate quantities is that, one, we have already noticed that calculation gets very much reduced. That our final answer theta does not depend on G, does not depend even on L. So long as the length of the rod and string are same, it does not depend on that length. These are interesting observations in the problem. And not only that, you can make a dimensional check of your final answer. Look here, my left hand side is a dimensionless quantity, and the right hand side should also be dimensionless. You check, the numerator is m square, and the denominator, well, I can now put the value of denominator here as the further quantity that comes from left hand side to right hand side, and both numerator and denominator are in square of mass, so it is dimensionless. So dimensionally this solution is correct, at least that much we can be pretty sure. And now I can put the numerical values. I write m square, which is 0.01, and then the first bracketed quantity you can check, it will be 0.22 into the second bracketed quantity is 0.18, and that makes it 1 by 3.76, and hence cos theta, which is 1 minus 1 by 3.76, is 2.76 by 3.76. You get theta immediately, which is cos inverse of 2.76 by 3.76, and you can check in your calculator that it comes to 42.8 degrees. Well, in the book the answer given is 41.7, but I think this is more correct an answer, where I didn't take G into account, I didn't take L into account, I have reduced the calculations, and finally I used the calculator to get the value of theta. So this is very interesting to observe that it's a problem where only angular momentum, and that too about a particular axis, that is the pivot through which the external impulse comes into play on the system. About that axis only the angular momentum is conserved, because torque of external impulse about that axis is 0. About no other axis the angular momentum is conserved. And this is how you get some interesting problems to work out here. Thank you.